afternoon. So I've had a talk with this title for a few years, but it keeps evolving. So this is actually quite different to a number of the versions that I've done before. And just for a bit of fun, because everybody gets exposed to the same languages all the time, I've been going through a phase recently of choosing the languages that people aren't using at a particular conference. So Michael just showed you a whole bunch of Ruby. I don't know whether you were using Ruby or not, but I'm going to use Python. And everybody always makes a point about certain things being very now or integrated with current thinking, but I'm going to go and use bits of C just to show you that it's not. I don't want to restrict your mindset to thinking that the techniques that I'm talking about here are related to a particular language or indeed a particular framework. Most of the examples aren't going to even use a framework because you don't need that. Okay? There is a myth that you need a framework in order to test. You don't. A framework will increase the reach and expressiveness and the ease of testing, but it will not change the possibility of what you can test. Okay? And people get too wrapped up in frameworks. A framework will give you a particular mindset, which is great when that mindset matches the problem. But the problem is that most people are using frameworks that were inspired by ideas in the 1990s or over 10 years ago and don't fit their current problems, and they're stuck with one way of testing and one mindset of testing. So we need to take a step back from that and ask, what do we want? So I'll get to explaining what guts are. Actually, no, I can explain it now. Good unit tests, but I'll get to explaining where that phrase came from. Let me think. Are these relevant? No, they're not really relevant. I don't think. No. Is this relevant? Possibly. Not entirely sure. Is this relevant? Yes, it is. So this is sometimes known as the Feynman problem-solving algorithm, named for Richard Feynman, the Nobel physicist. And it's kind of how a lot of people try to develop software. And we've kind of made an art form of this. You know, you write down the problem, think real hard, write down the solution. In fact, people have gone so far as to expand this into a project management style, known as the waterfall approach. Okay? Analysis, design, implementation. However, this clearly is not the complete story, because otherwise you end up with stuff like this. Just want to point out that in failure, software always loses its encapsulation. Oh, you're sitting there saying, oh, I've got state purity, I've got immutability, I've got privacy of my data items, you've got an error. Suddenly, your beautiful piece of encapsulation is dropped on the floor and it's cracked into pieces, and you can look at where the cracks are, and that tells you how something was built. It doesn't just tell you the language, it tells you the care. You cannot pay by PayPal for orders over £0. I think this is not going to be very useful. Now, I have a whole library of software failures. People now send them to me. I just used to take photographs and screenshots, but people now send them to me. I've got hundreds of these pictures. But the point there is that clearly these are things that are relatively easy to test. These are not the big things. These are the very simple things. These are what one project manager once described to me as stupid little programmer bugs. They're not being rude about programmers. They're just saying, we could have cleared it up just with a simple test case. And yet our system testers who are doing this manually and are actually end users trying to experience the system are being held up because of these little stupid programmer mistakes that we could have just mopped up very, very easily. So clearly there's a little bit more to this process than meets the eye. Check it. Unless you are, of course, a Nobel physicist, in which case you can feel free to opt out of that one. Okay, so we're going to check it. So and clearly this as an approach does not really expand well. It does not scale well. And we're not even entirely sure that it works anyway. But it doesn't scale well. So we take a different philosophy, and best described by the pragmatic programmers. Test early, test often, test automatically. If something's so important, if testing is important enough, why leave it till late? And why do it just once? Why make the assumption that you've got a big debt of tests to write? Debt metaphors have become very popular. I don't think we should just apply them to technical debt in the code, relating to code quality and questions of the architecture. I think there's a general idea, is that if you leave actions like this, writing tests, till later in a development cycle, and when I say cycle, I'm not just talking about some big waterfall thing, I'm also talking about Scrum. I'm talking about the rhythm of Scrum, the regular cycles. We will write the tests at the end of the sprint, or the worst case, we'll have a testing sprint. That's just wrong. But we will write the test at the end of the sprint. Don't build up a debt. Just get in there early. And if you're going to do this often, then do it automatically. Sometimes, when it comes to the bigger stuff, we're not entirely sure what we want to test. That's fine. Feel free to just experiment, but once you understand it, capture it, automate it. But here, how often? How early? Well, there is a fairly common mantra in test-driven development, the test-first approach. In fact, one of the vendors out there even has little stickers. I just picked up a couple of stickers for my kids. My boys, their bedroom doors are like a sort of wall of software development tools of the last decade and a half. They just put stickers on. I just come back from conferences, so I've got stuff dating going back 10 years on their doors now. It's kind of I think maybe we should give the doors to a museum at some point. This is advertising over the last decade. But one of them is red, green, refactor. Okay, so it's kind of very standard test-first cycle. Okay, the way people are often taught: red, write a failing test for a new feature; green, write enough code to pass the test; refactor, refine code and tests. Now, there are some issues here with the way that this is normally taught and explained, and I've had a problem with this for a long time. The problem is this is obviously the standard way of teaching people. That's why it ends up on a sticker as a standard piece of merchandising. And a lot of people are not entirely sure why it is they want to write a failing test, first of all, because, I mean, that's not a big challenge, is it? Write a test that fails. Yeah, I can do that. Yeah, big deal. Why am I doing that? Yeah, there's not a strong motivation. We've focused on an outcome that is actually not meaningful. So the focus here is not on intention, it's on events, and these events are irrelevant, quite frankly. Red and green, minor, not very interesting. But even when people get into this, sometimes they oversimplify it. And they get into the red-green rituals. The first trick is getting people to do the red-green thing, to just try it out for themselves, because most people will dismiss or criticize this without ever having really tried it. But when you get them to try it, they'll do this. But they're so busy focusing on red-green that they kind of forget the third bit. You can only hold a couple of things in your head as well. You know, that's it, you're done. And they kind of dumb it down, red-green. And it's just like, oh, yeah, and then they'll come up, well, I tried this test-first programming of yours. It's really stupid. It gave me really bad code. Yeah, it's a dumb idea. Oh, right, so what did you do? Yeah, I wrote a test that failed. I wrote enough code to pass it, and I wrote another test that failed. Okay, and at what point did you look at your test to see if they needed reworking, if you could spot trends in the code, and what was emerging? Did it give you pause for thought? Did you react to that thought? No, I just did test first. Quite literally, I wrote a test first, then I did something, then I wrote another test first, and that's it. It's like, okay, so you forgot to bring your brain to the keyboard. You are supposed to do that. I know it doesn't say that up there, but you are supposed to do that. Now, does anybody actually advocate this? Well, the problem is that with anything, when people are trying things out, they've got so many ideas in their heads, it's very difficult to keep them all running at once. And we often give people sound bites and helpful advice that, oh, sometimes it's not that helpful. Sometimes it's too easy to read the wrong thing. Uncle Bob has these 3 laws of TDD. You are not allowed to write any production code unless it is to make a failing unit test pass. You are not allowed to write any more of a unit test than is sufficient to fail. You are not allowed to write any more production code than is sufficient to pass the one failing unit test. There you go. Red, green, red, green, red, green, red, green. There is no hint of bringing your brain to the party. I have a very old school idea about what a law should be. A law should either be something that somebody is going to throw you in jail for if you transgress it, and I think that's a bit serious for a bit of code, or it's a fundamental principle of the universe. And I don't think this quite qualifies. So I'm a little hesitant to this. I understand what Uncle Bob's saying here. The problem is that when people sometimes read this literally, they end up with a very, very curious view. So in keeping with a theme that I've been running all week, actually, we're going to solve, we're going to tackle that great problem, fizzbuzz. Yeah, should be trivial for any would-be computer programmer. Okay, so let's do this. Let's do this out of the box. I'm going to write my first test case. Okay, I'm just going to write assertions. I'm not going to worry about structuring. Assert the fizzbuzz of 1 is 1. Okay, it's enough code to pass. Passes, green, we're good to go. Brilliant. 2, yep, change the code. 3, oh, fizz. Anything divisible by 3, fizz. And 4 is 4, anything divisible by 5 is buzz. You see, this is really classy code. We get all the way up to 15, which is divisible by both 3 and 5, and that's fizzbuzz. You've got a job for life if you write code like this, okay? And obviously, hang on, what was the problem spec? All the way up to 100, done. Okay, see, my tests are thorough. I have got 100% coverage. Okay, 100% coverage for the relevant domain of that function. And this is, it's not just statement coverage. Oh no, I've got 100% branch coverage as well. And as far as the state space is concerned, I've got 100% of that. This is brilliant. Tick all the boxes, ship it. Okay, and we've got as much test code. Sometimes people say we want as much test code as we have production code. Done. Yeah, this is ticking all of the right boxes, except there's a little bit of you that's thinking that's not really quite right. Okay, let's tidy it up. There you go, done. So now it does something reasonable outside. It just returns none in this particular case. That's what Python will do. Okay. And you're looking at that going like, well, I'm sure there's a better way of doing this. And you think, yeah, I know, because we're all about functional programming these days. So what I'm going to do is I'm going to have a dictionary of lambdas. There we go. That's a massive improvement. And then your colleague points out it's just a table lookup, which is slightly disappointing, but it turns out that table lookups are a surprisingly powerful and often overlooked technique. So yeah, there we go. And in fact, if you're feeling really smart, you might want to write a code generator to produce this. This is how you create enterprise code, by the way. Yeah, when you look at this, I'll create a code generator to create this, and this will solve our problems. No, it'll just multiply them by 100. So you're sitting there thinking like, okay, well, clearly this is actually why fizzbuzz was invented. We're all a bit embarrassed about actual real programming. Let's take another look at this. So let's try this test first thing again. Let's put that back in. Refine the code and test. Sometimes people just think it's about refine the code. I run TDD courses, I run workshops on unit testing and stuff like that. And one of the things that I'm guaranteed is that people will forget to look at their tests. What you will end up with is a story that starts at the top of the file. This is how we were thinking about testing. 30 minutes in, our test style has changed. 30 minutes later, our test style has changed. In the space of something like an hour and a half to 2 hours on a toy problem, you can end up with a set of tests that is already inconsistent. You let those people do this for 2 years, you'll be amazed at what you can get. And it's not good. The point here is that you're not just supposed to look at the code, you're supposed to look at your tests. Your tests are a form of education, you're learning about the problem. But again, there is a problem of dogma. Sometimes people get too wrapped up in the mechanism and the mechanics. A chap came up to me at a conference a couple of years ago, and he was a little bit concerned. He said, Kevlin, when it comes to test-driven development, what do you do if you have nothing to do on the third step? And I said, do you mean red-green refactor? He said, yes. And I was about to answer him, but he clearly didn't want an answer. He wanted to tell me. Because he said, sometimes I get to the third step, I get to the refactor step, and there is nothing to do. And he seemed worried about this. And he said, oh, so what I do is I make a little change that has no effect, and then the next time round I change it back. I kind of looked at him, and it was just like, I didn't do this in front of him, but in my head I did. That was a pure facepalm moment. And that's the point, is that what we've done is we've followed a ritual. Just as blindly as if we had not done a refactor, we have followed a ritual without consideration. The whole point of any technique, any pattern of practice, oh, I was wrong, the second slide is relevant, I use the word patterns. But a pattern of practice is a technique that is understood to work with an understanding of why it works and why it might not work and in what context it works and in one context it does not work. And the problem here is that we get sometimes so hung up on the mechanics of something that we forget that we're actually supposed to use these as channels for thinking instead of replacements for thinking. So this guy obviously interpreted as, you will refactor, whatever, you will refactor. So he took it as a command, whereas actually it's an invitation. It's a kind of an open question. It's like when you go up to, it's like when you go to the bar, as I'm sure some of you did last night. I certainly did. You go up to the bar and you turn to your colleague, drink? It's a question. Yeah? It's an invitation. Oh, no, I'm fine, I'm good. Oh, yes, please, I'll have, in fact, I think I had a tequila slammer last night. So thank you very much, Amanda Lauscher, for that one. So there is the idea of it's a question. Do we have anything to refactor? Is there anything to do here? If yes, please go ahead. Otherwise, move along. But I don't think this is particularly helpful. I have a bit of a problem with this as a kind of way of thinking about it. Although it's true, it's not a false structure. Let's try a different one. I'm going to borrow the Deming-Stewart cycle. Plan, do, study, act, sometimes rendered as plan, do, check, act. This is, if you like, the kind of the cycle at the heart of any agile or lean way of thinking, or should be. If you're not doing this, then there's something wrong with you'll find that there's something wrong with your overall approach. You will have the consequences of this. The idea is, plan is basically a statement. Here's what we're going to do. Then we're going to do it. Then we're going to take a step back. There's a pause. This is the whole idea. And it's important because sometimes people look at certain techniques and they say, this technique is going to slow me down if I do this. And people ask me, is it going to slow me down? And what they're hoping I'm going to say is no. But I say yes, which disappoints them. The whole point is to slow you down. Of course, it slows you down over the horizon of minutes and hours. The idea is that your acceleration is over the periods of weeks to months. That's the idea. The problem is that we're not very good at perceiving time. We're not very good at understanding time. So we normally live in the present, but actually the benefits are not in the minutes. They are in the days, the weeks, and so on. So there is this idea of slowing down. So I've done something, reflect on it. This is the role of a retrospective, for example, if we take a sprint cycle. And don't just think about it and talk about it. What are you going to do about it? Because it's not obvious sometimes what to do, but have a go. And then go around again. So what we've done here is we've taken the idea of the big picture. This is a kind of a general big picture process, and I'm going to just change it. The 4 R's, so to speak. Write a test. Here's a test. It's a plan for what I'm going to do over the next few minutes. This test demonstrates the usage. It captures my intention. Here is what I propose to build. It's a scope management mechanism. I'm not going to do more than this because I just want to focus on this. Oh, I've got a big idea about the bigger picture, but at the moment I'm going to focus on just what's in front of me. Now I'm going to make that work. Now I'm going to take a step back. I'm going to reflect on what it is. Are there any trends, anything that I'm spotting that is interesting, or interesting in a good way or interesting in a bad way, and therefore do I need to react and refactor that? So this is the idea here is that the PDSA cycle works at multiple levels of scale, from the minutes all the way through to the months. So a blog that Michael wrote a few years ago, 7 years ago, he made this observation about, so I've talked about the mechanics, but I don't want to linger on this idea of test-driven development, just the intention that no matter how we do it and in whatever sequence we do stuff, there is the idea of reflection and reasoning as integral to the act of testing. It's not merely check your code's okay. That really misses the point. But there's this idea, when you write unit tests, TDD style or after your development, you scrutinize, you think, and often you prevent problems without even encountering a test failure. So there's this idea of the very act of thinking about how you're going to test your code, or knowing that you're going to test your code, or actually doing the test, will change the approach that you take to your code. It will naturally slow you down in the short term, but it will make you think about why it is there, what it is there for. Now, the problem is that this idea of what we want from the test, as opposed to the mechanics, has got a little bit confused. Alistair Coburn, in the same year, 2008, made this observation. Very many people say TDD when they really mean I have good unit tests. And this is where the phrase comes from, I have guts. So the idea of programming with guts. And what he was trying to highlight is something that Ron Jeffries had observed, tried for years to explain what this was, but we never got a catchphrase for it. Now, Ron Jeffries was one of the original members of, or one of the original extreme programmers. And he observed, we don't have a catchphrase for it, now TDD is being watered down to mean guts. I encounter a lot of people who say, yeah, we're doing TDD, and well, they're not really doing TDD, and it's fair to say they're not doing test-driven development in the way we might think of it from a test-first programming point of view, but they're certainly doing something good, and their tests are great. And they're doing good stuff there. The problem is we don't have a proper word for that. But people are noticing they're doing something qualitatively different. So let's just focus on what makes a test good. So the first thing about making a test good, well, let's pick an example. I'm going to pick C because C is a lot of fun because it turns out you can do all kinds of stuff, like you can build the internet and you can also crash the internet using C. Buffer overruns are still in the top 20 security breaches that you get. And this is all down to the third letter of the alphabet. It is all down to C because it has basically unchecked memory rights. Okay, and I can run off the end of an array and quite happily overwrite things. It's all good fun, so we clearly don't want that to happen. Now, the other thing that I'm going to do is a very, very simple problem. What I want to do is I want to take an array of integers. So I'm going to point into memory. That's something to write. I'm not going to change it. That's why it's const. I'm going to point into memory. I'm going to say, here's the number of elements that I want to write. Because obviously with C, you have to tell it how many elements there are in an array. It's stupid enough not to know for certain reasons, for good history. And then we're going to write to an output. We're basically going to write a string, a sequence of characters starting at output, but no longer than length. It would be really good to not overrun that buffer either. Okay? So the idea here is we're going to take integers and we're going to write them out with comma separation. Now, comma separation is a trivial task. It's so trivial that kind of every now and then I come across a website that gets it wrong. In other words, they get the commas in the wrong place. They have a spare comma on the end or something like that. Now, this is trivial with a decent scripting language. You just go dot join and you're done. But if we're going to do this raw, let's find out how we're going to do this. We've got to describe what it is that we're going to do. Well, do we? I've got a function here. I've got 4 arguments. I need to count for what happens when I pass in null. What happens if I ask for no elements? What happens if I don't have enough output space? Well, that's an interesting question because it turns out there's multiple possibilities. So, here's an implementation in C99. Okay, don't worry about that. And here's an implementation in C++ that has exactly the same linkage and exactly the same behavior. Now, I've just made a very strong claim there. How do I know it's exactly the same? Because I thought really hard about it, because I closed my eyes and I thought, it feels good. A lot of programmers do that. How are you doing? Pretty good. And your code? Yep, we're kind of done. Kind of. Does it work? Yeah, I believe so. Belief. It's lovely stuff. I believe it does. Well, you need to turn belief into knowledge. Okay, and we do this by doing something like this, something empirical. This is the whole point of the plan, do, study, act, the Downing-Shewhart cycle. It is an empirical model. So let us find out. Okay, what we're going to do is we've got a function, therefore, logically in my head, I'm going to write a test function. Okay, function, boom, test. Okay, so it looks something like this. Okay, and you know what, and by the way, just notice there's a ... there, that's important. It goes on for a bit. It is as boring as it looks. It is just as unreadable, and trust me, if you can read C, it doesn't make any difference. You will fall asleep by the 5th line, okay? It's a good trick. If your kids can read code and they struggle to sleep, show them this, okay? And it's just like, oh, God, really? I mean, this might check that it's okay. And this is merely checking, okay? There's a big difference in my mind between, we're checking it's okay, and the biggest problem that we have is we have not communicated meaning. If you like, all of our software development practices are centered on many ideas. One of them is, can we get it to run? And the other is, do we know what it is that's running? Do we know what we mean? Are we having the same conversation? What are our concepts? Whether it's the 7 ineffective habits that I talked about last year, or this idea here of recovery of meaning. The biggest challenge here is not does it work, but what do you mean by it works? That's the challenge. What are we expecting here? And it's not entirely obvious. So somebody may come along and say, you know, Kevlin, the problem with your test code is you have no comments. Oh, that's obviously it. There we go. I put comments in. Okay, who reads comments? Let me think. Not the compiler and not the programmer. So there's your 2 audiences and neither of them's interested. okay? But you think, oh, well, maybe there's something here. I'm still lacking structure. We are driven by visual cues, okay? We care about things, visual spacing, visual reasoning. So let's do that. And now this also creates a separation, a logical separation. It also, scope-wise, it breaks out, it avoids any overrun from one test case, state change dripping into the next one. So this is really logical. So I've now got blocks, code blocks with comments. Do you know, I'm sure somebody invented something for that. Oh yes, functions. Yeah, so we now factor it out. So now what we've got is a series of named functions. Each of these functions captures and describes the intention of what it is what the body is trying to show. It's about recovery of meaning. It's not about checking it's okay. It's about telling you this is what we mean by okay. So we've gone from this to a recognition that there's this. So if you ever end up with I've got a function, now I've got a test, you also have an extra thing, a problem. Yeah? You never want this unless your function is hard-coded to return one value. You want multiple test cases against a function. And every now and then I get somebody saying, oh, well, but yeah, I could put them all in one function, as if somebody is paying tax on test functions. And if you are paying tax on tax functions, that's absolutely a fine way to solve that problem. But I don't think anybody's in that situation. Okay, let's move on a little bit. Let's go back to this. Let's look at let's open up one of these cases. Here, I've actually made a decision. Value, so I've got a value that I'm going to write to insufficient output. So this is the big question. What happens when I've got too little output space to write the full number? So if I've got the number 1,234, but I've only got 3 characters to write into, plus a null, then what am I going to do? Am I going to overrun? Well, I think we're doing this so that we don't overrun. Am I going to not write anything at all? In other words, take it in a more transactional approach. You either write everything or you write nothing at all. So if I don't have enough space to write 1, 2, 3, 4, I'm just going to have an empty string. Or do I truncate it and I just write 1, 2, 3? Now, I'll leave it to you to decide what you'd like, but the point here is that what I need to do to communicate to the reader is tell them, here's what I have decided, or me and my colleagues have decided, or the customer specifically requested, and I need to put that in there. It's not, is it right, is what do you mean by right? Value to insufficient output writes truncated value. Just reading that, oh, it's truncating it. Okay, fine, so I'm expecting that. Okay, and we write 42 in this particular case. I've got 2 characters to write out. Sadly, one of those needs to be for the null, and so therefore that won't work, so I should only write 4. The digit 4, and I should only write 1 character out. Now, some of you may look at that and go, oh, you know what, there's another problem here. I've just seen that I'm using 2 assertions. Has anybody come across that guideline? It keeps doing the rounds, that guideline that says you should not have more than 1 assertion in a test case. Anybody come across that? Yeah, it's surprisingly popular. It's completely wrong. But it is fairly popular. I dug it up on a blog here. The reason I've chosen this blog is not because it does anything wrong, but because of one of the responses to it. One of the things that Roy Osheroff warns against is multiple asserts in unit tests. Somebody else noted, proper unit tests should fail for exactly 1 reason. Yes. That's why you should be using 1 assert per unit test. No, that is wrong. And it's fundamentally wrong, and we can demonstrate exactly why this is the case. Here's my travel, just imagine we've got some code onto test. Here's my travel itinerary for the week. I started in Bristol, I went to Utrecht, and I ended up in Vilnius, okay? And this is what I'm expecting. So I can go ahead and I can write a single assertion, okay? That my itinerary that I've got from the code under test is exactly what I expected. No problem, 1 assertion. Let's break that down. That assertion is equivalent to assert that the resulting array is not null. Assert the resulting array has 3 elements in it. Assert that the 0th element, the first element, and the second element are Bristol, Utrecht, Vilnius. And assert that none of this throws. That's 6 assertions. Oh crap, we're going to have to break out the test. No. The point here is that this passes under all the circumstances the previous slide passes, and it fails under all the circumstances that the previous one. They are functionally equivalent. If you write your tests in a style that is so brittle that the smallest change of framework means you have to rewrite your test because you're following a foolish rule that says only have one assert, then you've got brittle tests. You don't have guts, you have butts, brittle unit tests, okay? Or bad unit tests. The point here is that we're focusing on the syntax, and the syntax there is, I was trying to say in the original one, is that I am writing a single character. I'm writing the character for. Now, I've got two ways of looking at that. I can split that out into two test cases, say I've written one character, or and another one that says, and I've also written out the number 4. It makes it look like they're two coincidentally unrelated things. They are the same thing. If you want to communicate to a reader that something is related, we have a really simple technique for that. We put things together. If you want to show somebody that something is unrelated, you put it apart. It's a very simple idea. And following a rule blindly, as we've discovered, is never a good idea. The other thing is I've had this discussion with a number of people, and they've been absolutely steadfast. They've said, you know what? No, we follow the one assert rule. And I said, do you use a mocking framework? Yes. Do you have more than one expectation? Yes. An expectation is an assertion, phrased for the future. Oh, but it's not spelt assert. You know, not every framework uses the word assert. It doesn't matter how it's spelt. It is a logical assertion, or rather it's a syntactic assertion. So this is the point. Roy doesn't recommend this at all. It's a misunderstood thing. My guideline is usually you test one logical concept per test. You can have multiple asserts on the same object. They will usually be the same concept being tested. One is a good starting point. You should be deeply suspicious of 0. One is a good and common result. Sometimes, though, what you need to express may be expressed in more than one syntactic assertion, even though it's one logical idea. Now, this is not news. Uncle Bob already talks about this. So 97 things every program should know. The Japanese edition is beautiful, but translated back into English for your convenience. He talks about the SRP thought, single responsibility principle. This is the idea. Cohesion is a principle that applies to test cases as well as other forms of code. This principle is often known as single responsibility principle, or SRP. In short, it says a subsystem, module, class, or even a function or a test should not have more than one reason to change. That's the goal here. It's a principle of cohesion. Now, going back to the test code, we can now see that these are this part of the same thing, and it's mostly because of the way that C is. Had I written this in a different language, this would have reduced to a single assertion because strings are a proper part of most languages. Okay? But in C, I want to make an extra point about this one. The result has to be, here are the bytes written, and I want to know that that correlates with the body. Now, if you look closely, I've used a little bit of font spacing here, but let's make this more explicit. There's a 3-part play here. There's a 3-act play, sometimes known as the 3 A's, arrange, act, assert. We're going to set stuff up, we're going to do the thing we're interested in, and then we're going to start saying things about it. Now, it turns out sometimes when you're dealing with something that is just a simple predicate, a simple function, sometimes these merge into one. And that's fine, but I want to pull out these 3 aspects that, at the very least, we will find that there are 3 aspects we can find. If you're doing behavior-driven development, this is directly equivalent to given, when, then, and I do prefer the BDD way of thinking about it. I find that's a little more useful. As Jason Gorman noted, there's nothing new under the sun. In fact, that seems to have been the theme of this conference. Given, when, then is what we call a Hoare triple. Tony Hoare made this observation when trying to formalize the consequence of statements of code. We have a piece of logic. We basically have some statement, some logical proposition before a statement of a truth. We have the statement of interest, and then we have a logical proposition following that must be true. So given that P is true, when we execute S, then Q must be true for this code to be correct. Given, when, then, it's identical. Now, given we're talking about logic, this is one of the books I learned logic from, and you can tell it's quite old just by the font usage. People just don't use interesting fonts anymore. The world is kind of either you end up with beautiful, elegant fonts, which I love dearly, or Comic Sans. This is very much of its time. I look at this and it says 1970s. It's all over. It's gorgeous. Newton Smith makes the observation, propositions are vehicles for stating how things are or might be. It's a proposition, it's a truth. And grammatically, only indicative sentences, ordinary sentences, in essence, which it makes sense to think of as being true or being false, are capable of expressing propositions. Now, what does that mean in practice? Well, if we go back and we take all the test names and take out the underscores, we see that these are all regular statements. Value to null output writes nothing. That is, if that's true, then we've succeeded. If that is not met, then we have failed. Okay, it's very simple. It's a proposition. Okay, let's take that the next step. The next step is obviously we go from just recognizing that we don't have a one-to-one relationship with functions. We don't also have a one-to-one relationship between tests and methods. This is a very popular problem. You go to Eclipse and you say, oh, please generate me some test stubs, and it'll go ahead and do you something like this. Probably the least useful form of code generation ever. I never want to have this kind of thing. You end up, in order to test how a method behaves, you need to have an object, and you need to interact with it, and you need to ask questions of the object, which basically means that you will end up with a very different approach. This also generalizes further. We can see it in terms of classes. Yeah? We have a very common thing. People say, oh yeah, I've got a one-to-one arrangement. In fact, you can see it in a lot of directories. We have foo, and we have foo tests. Yeah? We have a one-to-one correspondence between tests and classes, and we see this all over the place. That's not how you want to do it. This is how you want to do it. Here is a usage. I would like to use this particular piece of code in a particular way, and it happens to involve this class and that class. I want to use this piece of code for a different objective. It involves this class but not the other class, and so on. The idea here is you are cutting across the code. So this also leads to the question, of course, of coverage. Now, sometimes I've had pushback on this when I've said to people, oh yeah, don't structure your code don't structure your tests according to a one-to-one relationship with classes. But that's how our build tool works. Right, so you've just told me the problem. What are you going to do about the solution? Yeah? People think that that's the end of the conversation. That's how our build tool works. Or everybody understands that. That's great. You've now described the problem, not the solution. Now figure out a solution. Other questions pop up when people are always asking about the amount of this kind of stuff. I want to talk about coverage. Martin Fowler observed, from time to time I hear people asking what value of test coverage, also called code coverage, they should aim for, stating their code coverage levels with pride. In fact, something that Martin doesn't mention here, and one of the things that really annoys me, is that people use the word code coverage and they never tell you what form of coverage. Okay? There is a default that everybody uses. The default is statement coverage. And the reason people quote this is, one, it's easy to get a high number, and two, it's easy to get that number. The minute you head off into branch coverage, path coverage, and all these other forms of coverage, it gets a bit trickier. But when people quote high levels, they are normally quoting statement coverage. In other words, my tests touch this statement at least once. That's all you're saying, which is better than 0 times, but it's not a great way of thinking about it. You need to be specific. When somebody says code coverage, you say, what kind of code coverage? And they kind of look at you blankly. And then you say, right, now maybe before you quote the number at me, you should learn what code coverage is. That's a great conversation stopper, okay? Such statements miss the point. In the same article, he quotes Brian Marrick. I expect a high level of coverage. Sometimes managers require one. There's a subtle difference. Now, one of the things I do as a bit of a hobby, and it's Friday today, is I do this Facebook page, Word Friday, where I put up unusual words or things about language. And one of the ones I put up a few years back was Goodhart's Law, which fits this description, this problem that we find with coverage perfectly. Once a metric becomes a target, it loses its meaning as a measure. If I offer you and I say, look, we've got 90% statement coverage, that's a statement about statement coverage. I think I'm using the word statement too often there. If somebody comes up to me and says we need to get that to 95%, now we have a problem, because now we're pushing on an observation. We're pushing on an observation. A metric, as he observed, it's named after an economist, Charles Goodhart, and his exact quote was, any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. The minute you start saying things like, we need to reach this, and we're going to do everything to reach that, and even worse, when you attach money to it, and I've encountered that in a couple of companies, when we reach this, the team gets a bonus. Whoa, okay, your metric is now meaningless. Okay, it has lost any value it ever had. So we need to be very, very careful. It doesn't mean that you don't care about it. You do care about it. It's just that what do you do with that knowledge? So let's go back into some code fragments and code examples and observe that Leo Tolstoy, apart from writing very, very long books, was in fact a programmer. He was highly aware of the fact that when a piece of code works, its happy day scenario is well defined. But how many ways can it fail? Each unhappy family is unhappy in its own way. There are many ways something can fail. The problem is that when it comes to testing, people have a very simple block attitude. So here is a very simple set of tests to deal with an ISBN type, International Standard Book Number, which is a code that you'll find on the back of any book. You can go to Amazon and see these codes. And it has a rule of well-formedness, which basically means if you pass in an invalid ISBN, it should get rejected with an exception, the malformed exception. Now, I've got, it's all nicely structured here. I've got strings for tests. Instead of using function names, I'm now using strings. And I've got a proposition, so I'm using the term proposition. This is just an ad hoc C++11 testing framework. C++11 supports lambdas and this kind of stuff. And it fits on a slide, if you care. And what we've got here, the real problem here is not that I'm testing. Again, I've lost the meaning. Where's the intention? Let's look at it. Look at that. That is one of the most common ways that people express. Here is where I'm testing the validation code. I've got a test called test validation. And you kind of point out, well, what does that mean? I don't know what you mean by validation. What are the rules of well-formedness for an ISBN? You can't tell looking at the example. I mean, there's 4 examples there. Can you tell what's wrong with each one? You might be able to guess a couple. But it's not immediately obvious. And you tell somebody, look, this test validation, what does that actually mean? You haven't told me what your intention is. I know what my intention is. I want to test validation works. If you ever, and every now and then you'll find it's guaranteed in every test suite, you'll end up with something, test that blah, blah, blah works. It's like, okay, unless you're going to actually reasonably have a test that says test that something doesn't work, this is a meaningless statement. So let's try something else. Let's try breaking it up. Oh, okay. Again, we're not being taxed for these things. ISBNs with more than 13 digits are malformed. ISBNs with fewer than 13 digits are malformed. ISBNs with non-digits are malformed. By the way, I've simplified the rules for ISBNs a little bit here. ISBNs with an incorrect check digit are malformed. It has a check digit at the end, calculated based on the previous 12 digits. So now we've learned something about ISBNs, and that's exactly how it should be. You should be able to read the tests, and you learn the domain. In fact, I've been very, very careful to be utterly consistent. I've used the language malformed here because the exception is called malformed. Or I named the exception malformed because I used the language malformed. Don't use the word illegal here if you're going to use the word malformed here, or vice versa. Your opportunity here is to communicate and use the language of the domain with some kind of consistency. So there is this very simple idea that we get into that, as noted by Nat Price and Steve Freeman, authors of the book Growing Object-Oriented Software Guided by Tests, for the blurb for a workshop they did a few years back, Are Your Tests Really Driving Your Development? They made this point. Tests that are not written with their role of specifications in mind can be very confusing to read. The difficulty in understanding what they are testing can greatly reduce the velocity at which a code base can be changed. Quite simply because you're looking at the code and you say, I don't know what I'm expecting. I mean, the test will fail if I get something wrong. I mean, it's nice to have the test, but I don't know why. Now, what do you do with a test that you're not sure of the meaning? You know, I'm busy going along and I make some changes and some tests break, and I go and look at the tests and I kind of, well, I don't know what this test is trying to tell me other than red, which is not very helpful. So you look at it and you look at the code and you think, you know what, I think the code's all right. I think it's all right. Okay, what are we going to do with this test case? I know, I'll put ignore on it, or I'll comment it out, and that's it. That's the end of the life of that test case. Oh, it may sit around like a zombie in the source in your source control system for a few years, but that's its fate. Nobody's going to go back in there and say, oh, I'm going to review this and see if I can bring it back to life, resurrect it. No, they're not going to do that. So let's have a look at one of my favorite problems. It's a nice small problem. So a piece of C#, something that classifies when is a year a leap year. Okay. My experience tells me that when you ask software developers, roughly between 5 and 10% of people know the full rule for the Gregorian leap year. Okay. Just as a side note, don't do your own date handling unless you are a total date nerd. Okay, you'd be surprised how weird date and time handling can get. But we're just going to focus on one seemingly simple problem. But as I said, the number of people that actually know this is typically kind of 1 in 10, 1 in 20 amongst software developers. Amongst the larger population, it's even lower. So the goal here is not to test that it is correct. The goal here is to communicate to the reader, what do we mean by correct? What do you mean by leap year? Leap year is a concept. Tell me about it. Okay, so first thing we learn is that there are 4 kinds of year, not 2, leap years, non-leap years. There are years that are not divisible by 4. They have a particular classification. There are years divisible by 4 but not by 100. Those are interesting. Years divisible by 100 but not by 400, and years divisible by 400. There are 4 categories. Yeah? Okay. You're going to run out of reading ability if you keep using camel case here. It's common in a number of languages to use camel case, but quite frankly, when you start writing out propositions, you're going to end up with sentences. So I'm going to use underscores even if that's against the language conventions, because it's a test convention. It's not a production code convention in that environment, it's a test convention. Okay, so we've got that. Okay, let's do something else. Let's follow a BDD habit. A BDD habit is often to put the word should in there. Years not divisible by 4 should not be leap years. Years divisible by 4 but not by 100 should be leap years. So this year was not divisible by 4, and there was no 29th of February. Next year is divisible by 4, but it's not a multiple of 100, and it will be a leap year. The problem is, this word should. One of the things, I'm a writer, and I dislike noisy words. And in fact, I'm not the only one. Strunk and White, who wrote kind of the classic book on English writing style of the 20th century, make definite assertions. Guess what? It wasn't just Tolstoy that wrote about tests. It turns out Strunk and White wrote about test cases as well. Make definite assertions. Avoid tame, colorless, hesitating, non-committal language. Should. What does that mean? You know, years not divisible by 4 should not be leap years. In English, should means, yeah, but it might be. You know? I mean, I should finish in 10 minutes, but I might overrun by a minute, you know? But, you know, oh yeah, the leap year code, you know, sometimes it misclassifies a leap year, but it's okay. It should be okay most of the time. No, should is the language of hesitation. It's a failure to communicate. You use words like should to build up a sentence to hide what it means. It's just like, no, get direct. No, just say what it is. Years not divisible by 4 are not leap years. And if somebody says, oh, you know what, actually we've got a contradiction to that rule, fine, because they've observed it. You've made a statement and they've said that's not a true statement. It's a proposition. This is logic. And one of the nice consequences of naming your test like this is, apart from having to overuse, you don't overuse the word should, but your test names are a bit shorter, your English is more direct, and also when your tests run, the names are a listing of the properties of your code. All the things that are green are true of your code. And if they're red, then that is a thing that is not true. In other words, you can take the name and you just negate it. Years divisible by 100 but not by 400, like 1900, are not leap years. Well, apparently they are, according to this. In other words, the problem is exactly the opposite of the name. It's really easy. I don't know why I've got the problem, but I can tell you what the problem is. Okay, so let's look at some other test naming styles. Sometimes people really go to town with the BDD and say, oh, we're going to structure all of our tests using given, when, then. And you run out of right-hand margin. I mean, here you must really, did you hate your English teacher so much? Did you really, really hate them? Because this just shows a complete disrespect for human communication and the person that taught you. Okay? This is just bad English. Given a year, when it is not divisible by 4, then it is not a, oh, for God's sakes. Omit needless words. Strunk and White, back to there. This is better. Given a year not divisible by 4, then it is not a leap year. That's better. Because there is no when, there's no action, it's just a truth. I'm not doing anything, it just is. It is or is not, okay? Okay, so the point here is that when we use the language more directly, when a sentence is made stronger, it usually becomes shorter. Brevity is a byproduct of vigor. You're trying to say exactly what you mean, which is a very hard thing to do, but that's what we're trying to get out of this. Now, we might wish to break things and use some name structuring. So here, using NUnit, I'm taking advantage of test fixtures that are not aligned one-to-one with a class or a method or anything. I'm just using it because I can get hierarchy. And hierarchical structuring and grouping is a very natural thing to programmers, but it seems to be something that people are relatively reluctant to do in traditional test cases. Some of the newer test frameworks are a little bit better at supporting this reasoning and this presentation, but it's something that you can, you really want to value, because what you get is, leap year spec, given a year not divisible by 4, then it is not a leap year. Given a year divisible by 4 but not by 100, then it is a leap year. But there's a problem with this. Although it's kind of all there, this is not actually how people think about the leap year problem. It's not a given and then there's a result. The way that people start up, typically with classifiers, is things are or are not something. So the opening position, the English is back to front. When is a year a leap year? It's not given as something, then it's a leap year. When, a year is a leap year, when is it a leap year? Yeah, we open the other way, which looks like this. A year is a leap year if it is divisible by 4 but not by 100. Or a year is a leap year if it is divisible by 400. A year is not a leap year if it is not. In other words, the English is more direct, but we've inverted it. We put the classification up front. In other cases, you will find that you want to use the previous approach. In other words, you need to be sensitive to the problem that you're working with. Yeah? So don't get stuck in a fixed pattern of naming. Now, sometimes a fixed pattern of naming can help. I've had people ask me about this, and I always, we're naming things using a given when-then style. Is that a good thing or a bad thing, Kevlin? I don't know. I can't tell you. Okay, let me ask you a question. Are your test names messy and chaotic? If the answer is yes, then having a fixed approach is a really good idea because it will bring order to chaos. On the other hand, if you've been using a fixed naming style and you're finding it's getting verbose and doesn't fit all of the things you want to talk about, then now's the time to move on. You've now learnt enough to know what to express. Now, something else that's worth noting here is if you're paying very close attention, you'll have seen that there were parentheses at the end. Rather than just empty, they are filled. And what's going on here? Well, I'm actually driving this using some data. Now, it's a decent testing framework, like NUnit, it's pretty decent on this one. JUnit sucks, which is why there's a JUnit Lambda project to upgrade it. But here I can actually choose specific examples. I can choose 2012, 1984, and 4 as examples of years divisible by 4 but not by 100. I can also use a very simple generator range from year 400 up to and including 2400 in steps of 400. Okay? So I've got a very simple approach there to dealing with this stuff. Now sometimes when people start to get general with their tests, they say, oh, okay, I've got it. I'm now going to have, I see what you're doing here, but I think I could put all of these in one test case. And I'm going to call it, a year is either a leap year or not. Well, I think that pretty much covers all the possibilities for a Boolean. And then I'm going to have a function called is leap year is correct, which is just another way of saying is leap year works. Okay? And I'm going to cover 10,000 years, so I'm going to get better coverage than your code, Kevlin. Oh, sure, that's great. So what does your test case look like? I need to put this up here because I need to tell people when they look at the PDF. No, don't do this. Okay, so that's obvious, really, isn't it? You're looking like, oh, well, that's it. There's only one problem. Well, let's factor out the logic there. Let's just get rid of that logic. Let's call it leap year expectation. And there is my leap year expectation. There's only one problem. It's identical to the implementation. Well done, you've come full circle. This is the problem sometimes people get when they overgeneralize stuff. They end up having to repeat all the logic on the inside, and therefore they will probably copy and paste that logic. Oh. And you will have successfully asserted true, true. Yeah? Okay. So there is a different way of looking at this. And that different way is to start, there's a different way of reasoning about it. We've looked at the idea that you want to express intention. We've looked at the idea you can have an example, that's the CSV code, but we've also looked at the idea you can parameterize with generated or explicit values, and we can take that a step further. And you'll notice the naming there moves us towards, in fact, all naming in some way reflects a property of the code, but we can generalize this further, as you can see in a number of functional testing frameworks, to the idea of actually let's describe the properties of the thing as a whole. The danger of that is that you are more likely to get it wrong. The benefit of that is sometimes it will give you the thoroughness that you desire, and it will also allow you a different approach to the code that doesn't work if you build up one example at a time. So you need to sense your way, you need to feel your way. What kind of problem is this? What kind of testing approach would most benefit this code? So there's not one rule for everything, one rule to ring them all. So let's go back and look at fizzbuzz. So here's an implementation in Python. It's a bit boring. It works, but it's a bit boring. It modifies and accumulates state in a string called result, and yeah, whatever. I prefer this one, because this one fits in a tweet, and there's enough space for a hashtag, so you can make rude remarks about that tweet. I like this one because you can't do it in any other language other than Python, pretty much. It's totally gratuitous. And if you understand this, you understand Python. If you don't understand Python, then you won't understand this. I'm not going to explain it, but let me just say that it takes some great liberties with the idea of what a Boolean is. But that lies at the heart of Python. So it's very Pythonic in one sense. Okay, so how do I know that both of these are equivalent? I've given you two things, and I've said, yeah, they're the same. What I'm going to do is the range is specified. It's a closed problem, 1 to 100. And here I can actually generate all the values. What I'm going to do is I'm going to have a list of all the results from 1 to 100. And we saw that earlier. If you want to refer back to the earlier slide, remember you type it out one at a time. But here I'm going to just take fizzbuzz and I'm going to generate that. Here are the actual results. And then there are a set of truths that I want to assert about this. There must be a number of things that are true of these 100 elements. And then I want all of these to be true. Okay? So in other words, that's kind of a universal quantifier. All of the things I'm going to say. What are the things I want? Every result is fizzbuzz, or a decimal string. Okay? That's got to be true. So we're not allowing anything else. Hello world is not permitted in this set. Okay? Non-strings are not permitted in this set. Every decimal result corresponds to its ordinal position. So if you find a number, say 13, then it should be the 13th position in, as if counting from 1. Every third result contains fizz. Okay, so the third one should be fizz. The 15th one should contain fizz, because it's fizzbuzz. Every fifth result contains buzz. Every 15th result is fizzbuzz. No decimal result is divisible by 3. If you see a number, it should not be divisible by 3. If you see a number, it should not be divisible by 5. The ordinal position of every fizz result is divisible by 3. The ordinal position of every buzz result is divisible by 5. And the ordinal position of every fizzbuzz result is divisible by 15. These are the properties that must be true, necessarily, of those results. And then we can just turn it into Python. And there we go. Bang. If you want to keep the strings around, you can put this in a dictionary, or you can do a couple of other things. But the key idea here, and hopefully what's been demonstrated, is that we've kind of shifted in styles. But what I've done is I've explored each of these, and they all have something in common. All of the test styles that I've looked at, they satisfy an idea of good unit test. And what am I calling a good unit test? I'm saying a good unit test is one where we express intention of code usage with respect to data. But we might do it differently. We express the intention using names and grouping and nesting. We have a code usage example that realizes the intent. It's the code version of what the name is trying to say. And we might illustrate that with one example or many. And that example might be explicit. Those examples might be explicit, as I did in the first example where I just used a single example, or even in the leap year where I used 2012, 1984, and 4. Those are 3 explicit examples, or alternatively I might generate them. And there's a whole load of things that we can talk about generation. But basically, a good unit test has these properties. There's what is it that we're trying to show with respect to what code, with respect to the values that we can pass through it. And most testing frameworks don't make these 3 aspects visible. They normally concentrate on 2. The weakness of that particular last Python example was code usage, respect to data, but we lacked intention. Okay, although I sketched it out on the slide before, that's what would make that a good unit test rather than one that is thorough. Thank you very much for your time.